Every fact and figure in this video is sourced directly from comprehensive research papers and government reports linked below. We highly recommend watching all the way through to truly understand the scale of the engineering challenge ahead. Since 2014, India has added 299 gigawatts of fresh generation capacity, shifting the country from a structural power deficit to a consistent surplus. The current roadmap targets 500 gigawatts of non-fossil capacity by 2030. But relying strictly on solar and wind power introduces a massive engineering problem. The sun goes down and wind stops blowing. That intermittency threatens to break the entire system. This animated diagram maps the duck curve over a 24-hour period. Midday solar energy floods the grid with electricity, but at sunset you get a steep drop in generation, just as millions turn on their lights, creating destabilizing voltage swings. Bridging that gap requires a way to shift bulk energy across entire diurnal cycles. While chemical batteries manage short-term flickers, the magnitude of this demand is forcing engineers to investigate mechanical gravitational storage. If you want to dive deeper into the massive infrastructural challenges of the 21st century, hit the like button and subscribe to The Explainer. Stabilizing the national grid now depends on engineering large-scale mechanical systems. These are massive, 100-year storage assets designed to anchor the nation's power supply. Meet pumped storage hydropower, or PSH. Instead of relying on lithium and chemistry, these giant water batteries store power using water, elevation, and gravity. This cross-section schematic illustrates the off-peak charging cycle. During midday, surplus solar electricity is used to literally pump water from a lower reservoir up a mountain into a higher one. Post-sunset, the cycle reverses. During peak evening demand, gravity takes over. The stored water falls back down through reversible turbines, generating firm, highly dispatchable electricity. Because battery module costs have plummeted, it's widely assumed that massive arrays of modern lithium-ion batteries are the optimal choice for grid storage. But that ignores the levelized cost of storage, calculating the true life cycle cost of an asset. Chemical batteries suffer capacity fade, rely on imported supply chains, require expensive modular replacements, and die out within 15 years. When you need to balance a massive grid for more than 6 to 8 hours, water mathematically outcompetes lithium. These giant pumped storage facilities offer massive mechanical inertia and a 100-year operational lifespan with absolutely zero capacity fade. Despite these advantages, India's pumped storage pipeline was heavily blocked. The government legally treated these massive batteries exactly like highly disruptive conventional hydroelectric projects. That meant damming up active rivers, triggering complex environmental appraisals, and navigating contentious interstate water-sharing disputes. That regulatory blockade was systematically dismantled on April 4, 2026. The government officially decoupled pumped storage from conventional hydro, decentralized the approval process, and aggressively waived interstate transmission charges for energy storage projects. The single most consequential maneuver in this policy was a blanket regulatory exemption for a specific architectural design, off-stream closed-loop systems. This top-down schematic contrasts the two approaches. Instead of intercepting natural water flows like the active river dam on the left, an off-stream closed-loop system cycles a fixed volume of water between two artificial reservoirs, completely isolated from natural river networks and ecosystems. This geographical freedom allows engineers to innovate. Developers are now surveying abandoned, deep underground coal mines for a new purpose. They intend to repurpose these immense subterranean voids as lower reservoirs. By legally and structurally removing natural rivers from the equation, the April 2026 policy cleared away decades of environmental friction. This single pivot successfully flooded the construction pipeline with gigawatt-scale private capital. The market reaction to the new framework was immediate. Private capital and independent power producers aggressively entered the space, and they now control roughly 70% of India's massive capacity pipeline. Individual states are taking highly distinct approaches. Gujarat built a highly structured, four-tiered capacity market to separate state energy requirements from open market commercial projects. Meanwhile, Tamil Nadu is engineering complex hybrid models, directly coupling wind and solar farms to nearby pumped storage to smooth out their seasonal generation gaps. But this rapid scale-out faces severe geographical hurdles. The prime topographies for these projects, specifically the Western Ghats, heavily overlap with eco-sensitive zones. Digging massive tunnels and clearing transmission corridors pits the mandate for clean energy directly against the need for strict biodiversity preservation. There are also critical industrial vulnerabilities. These projects rely on highly specialized variable-speed pump turbines capable of tracking minute fluctuations in grid frequency. Sourcing these requires advanced metallurgy, forcing the domestic heavy machinery sector to indigenize its manufacturing to avoid relying on strategic imports. Deploying these megaprojects is a volatile balancing act. It requires navigating fragile local ecologies and pushing the absolute limits of raw industrial manufacturing. The national roadmap dictates commissioning 100 gigawatts of pumped storage capacity by 2035. That demands an aggressive build rate, averaging 9 gigawatts of capacity annually for the next decade. This project hinges on mastering the temporal dynamics of electricity, physically holding immense power at midday to dispatch it exactly when the grid demands it 12 hours later. India is currently moving mountains and excavating geography to build this infrastructure. The result will be a clean energy grid secured by the physical weight of water, engineered to remain resilient for the next century.